Hello everyone. Today we'll be going over the paper method for implementing log-free shared data structure written by Greg Barnes. So the paper focuses on log-free universal construction for large objects using coordination technique and caching algorithm. So the paper mainly describes approach to universal construction, but then it doesn't give you a solid implementation on any data structure. So in order to understand this paper well, I tried implementing the ideas on linked list. Might not be 100% correct, but at least it gives the audience a better understanding of what's going on. Yet another universal construction. Yak. That was what I felt when I started reading this paper right after Hurley's universal construction. So Hurley's paper describes universal construction for log-free and weight-free data structures. And just after that, when I started reading this paper, I wanted to know what was it that we are gaining in this paper. So in order to truly appreciate the work, I would recommend you go over Hurley's universal construction paper first. But if not, I'll have a quick recap of what's there in universal Hurley's paper. So Hurley's universal construction. So basically, we'll be only covering log-free OC universal construction and will not be covering the weight-free universal construction. And in the paper, he describes two log-free algorithms. One was for small objects. Small objects are essentially objects that can be copied to the process local memory, and large objects are objects which cannot be copied. It doesn't. The cost of copying is more than the actual sequential operation. So yeah, so this is the basic idea for log-free UC on small objects. So we read pointer to the shared object using load linked. We copy the current version to our private memory block. We apply the sequential operation on the copy, and then we call the store conditional to have the update from our local copy to the shared copy. So essentially, after performing the sequential operation, we have a new version of the data object in our private copy. We use store conditional to swap the pointers and then make it available in the public, or make it available to everyone. And if the process fails, then we repeat step 1. For the large objects, it is too large to be copied, and that becomes a bottleneck. So Lee's suggestions were basically converting large objects into fragments. So fragments are nothing but a group of items, and now the basic unit of copying becomes fragments rather than copying the entire data structure. So let me Alright, so large objects is fragmented into blocks, and then an operations are implemented only on those blocks that must be accessed or modified, and they are the one that's copied. And yeah, sequential operations are written in a functional style where if particular operation is to modify, then it is not done in place, rather you create a logically distinct version and then make the changes. So this would be the suggested large object protocol. Basically, we read the objects which are required for our operation using load linked. We copy the blocks into our local copy. And the cost of copying is still unaddressed, but then yeah, we copy the blocks into our local copy. We do the sequential operation, and then once that is done, we get a new version of the objects. We call store conditional to swing the pointers from old version to the new version. After this, the paper starts talking about memory management using memory pool. So whenever you copy the blocks into the process memory. You are not allocating a new memory as such for the block. You will be reusing memory blocks which are there in the memory pool of that process. So by going over this memory management hack, you are essentially uh, avoiding new allocations, which is kind of expensive, new memory allocations which are kind of expensive. And also, if the process exhaust allocating local blocks, and in that case it can lend from shared pool, which is quite expensive, but then that's also an option. So these are some snips from Haley's paper. So here you see that like in the portion where he describes about the logical copy and then things like that, and then finally in the conclusion he mentions that copying algorithm, or the cost of copying, should be the responsibility of the programmer, and then correctness is the responsibility of the system. So this gives a lot of like lot of responsibility on the programmer to kind of figure out effective copying algorithm, but then that's how it is. So now let's go over two problems that we face in the release approach. So one is expensive copying. So let's go over an example. So in this case, we have a linked list. We have 4 elements, 1, 2, 3, and 4. And initially all of them are having v1 as the version number. Let's say we want to modify head. So in that case, you modify head by creating a copy of the head node into your local copy, and you modify the node, and then finally you swap back the new version with the old version. So here you can see that the copy set is just head node rather than like the whole data structure. So effectively you're only copying the node which you are going to modify. That's the best case scenario. But let's see the worst case scenario. We have the original list on top, and then we are modifying the tail instead of head. Now when we modify 4 to 5, essentially 5 now becomes v2. Alright. So now 3's next pointer should be pointing to the v2 version of the node. But then that would mean that essentially 3 needs to be updated with that change. So 3 needs to be converted to v2 as well by modifying the next pointer. Now that will force 2 to be 2 also to modify its next pointer, and then 1 as well, and then like if you see recursively it forces all the node elements or all the linked list elements to be copied into our local copy. So in the worst case, we see that the total copying required would be the entire data structure. Let's take example of doubly linked list. So in this case, like I haven't drawn the example for doubly linked list, but then it's similar. So in the doubly linked list, each of these edges will be double-ended. So 1 will be pointing to 3 as 2 will be pointing to 3, as well as 3 will be pointing to 2. So in that scenario, when a 2 is modified, so its neighbors 1 and 3 needs to be modified as well, because the next pointer should be modified, or the next or the previous pointer should be modified, and this eventually recurses, and then you will end up copying the entire data structure as in doubly linked list. Let's take the example for tree scenario. So in this case, we want to modify the leaf element, which is 5. So when we want to modify 5, we traverse from root to the leaf, and then we copy all the elements in that path. We modify the 5, and then like use show conditional to swap out the original list, swap out the path from the original shared data structure. So as you can see, 3, 6, 4, 5, 4 and 5 are there in the copy set, and then you modify 5 to 6, and then like finally after the operation is done, you copy it back to the shared data structure. So copying algorithm for Hurley's. So though it's not called officially copying algorithm, but then for the sake of this discussion, let's call it as copying algorithm. So the main logic is, for a random access data structure, we copy the entire data structure as such, and for a pointer based data structure, we copy only elements that are changed, and recursively all the elements that points to that data structure, points to that node, right? So in this case, the cost of copying is t plus c for each of the operation, where t is the sequential cost of the operation and c is the time needed to make logical copy of the data structure. It is quite expensive when compared to the caching method, which will be discussed later in the slides. But yeah. Problem 2 was concurrent updates. So generally how it's dealt is, when we want to introduce concurrency in a lock-free data structure, uh, we essentially take one of the two routes. The first route is by proving that specific set of operations by two threads working on the same portion of the operation do not same portion of the data structure do not substantially interfere with each other, or by preventing such interactions. Release does the second one. So it prevents basically uh, interfering operations, and that is kind of a bottleneck for concurrency. Let's say in this case 1, 2, 3, and 4. Let's say we want to modify 3 and 4 nodes, and we want to make it as 6 and 5. So uh, when we modify 4 to 5, we'll be like copying the entire object set, and then we'll be making the changes on the entire object set. We'll be doing store conditional on each of the entire each of these nodes. So if uh, if the second thread succeeded in making 3 to 6, then in that case the operation performed by on this 4 would be aborted and retried. So essentially the gist is, only one thread is trying to update the data structure, is actually doing a useful work at a particular time, so it's never achieving a better throughput than the original sequential implementation. Alright, so now we'll discuss about cache-based universal construction. Let's go over the key benefits. The first thing is basically the cost of operation. So cost of one operation is essentially converted drastically reduced from t plus c to t log t, where t is the sequential cost of operation, and it also allows concurrent updates, which Hurley's method doesn't. So the ideal lock-free universal construction has four features. One is it should be general, it should be simple, it should be efficient, and it should be flexible. Generally, a universal construction for all the data structure doesn't uh, uh, work well for all the parameters, but the author claims that this universal construction that we are going to cover is essentially checking on all the, like, essentially good with all the features that we have listed here. So technique 1, cooperative technique. So this paper will discuss two techniques. One is cooperative technique and the other is caching technique. We'll discuss about cooperative technique first. So since we discussed in the last slide thread interference, these are the main observations that the author made regarding thread interference. There are multiple threads which want to modify the same portion of the data structure, and creating new version every time is the problem. So what if we can do it in place, and instead of using locks, what if we have another way of doing things? And also uh, holding a lock and then going on a halt will force other threads to wait as well. That's called convoying. Yeah, author doesn't want that, because essentially this is entirely a lock free data structure, so someone has to progress. So In order to make that progress, the author provides an idea of uh, each thread writing down exactly what they are going to do on that shared data structure, so that like if at all there is a thread which locked a particular entry and then went on a halt, other threads who want to access that node can essentially have some means of completing the first thread's work and then like proceeding with their operation. So that's essentially the gist of cooperative technique. We'll be discussing it in more details in the subsequent slide, but then the approach is that if T1 wishes to change some portion of the data structure, and it first checks whether another thread T2 was already working there. If so, then T1 reads T2's information and cooperates to complete T2's work. So what are the changes that we need to incorporate in order to like make a process cooperative? So there are two changes. One is on the data structure side and the other is on the process side. So let's first go over the data structure side. So this is a normal linked list. If we are having uh, fine-grained locking enabled on a linked list, basically we'll be having each node having a individual lock, and for a process to claim a particular node, it will use the lock in that particular node and then uh, make the changes. In the new linked list, what we'll be converting is essentially the on top we have the original linked list, and on the bottom we have the new linked list. So 1 2 3 and 4 are still there. It's we still maintain the linked list as it is, and instead of lock we have op pointer. Op pointer is a pointer which essentially points to an op description, and op description will be containing program counter plus the operations that you need to perform, like that the process needs to perform. So we'll be covering that in detail in the subsequent slides, but then this is like on a high level what it would look like. So here if you see, we have considered one node as one block, but it need not be the case. Cell contains one linked list item. Based on the fragmentation rule that Hurley proposed, we can have multiple linked list item inside a cell. So it could be that we have 1 and 2 in one cell 1 and then 3 and 4 in cell 2. And similarly, in the case of new linked list, we can have instead of lock we can have op pointer for the cell, and then like 1 and 2 will have a shared op pointer entry. This is kind of similar to database blocks. So instead of reading and writing just one record, we in database world uses blocks to make operation on a particular record. So whenever we want to read a record, we'll be reading the block first and then modifying the change. Similarly, it can be thought of something similar to the blocks. And we also have two-phase locking. So essentially two-phase locking involves locking those blocks that you want to modify. So the first linked list which is having a lock on these two entries can be thought of as two-phase locking implementation kind of approach. So yeah, if you want to write something to the record, or if you want to modify that linked list node, then you can uh, log the particular block and then do the operations. So this is how a thread would claim an node. So when P1 needs to claim item 1, it tries to put an op description in the op pointer 1, and if P2 needs to claim item 1, it tries to put the op description as well, but then it finds that op item 1 is already logged by P1, so P2 cooperates to complete the associated operation and then begins again. That is, P2 does P1's operation. Maybe we can think that P1 was stalled in the middle and then like P1 was not able to complete its operation. So in order to avoid the convoying effect, P2 does P1's job first and then proceed with P2's job. So there are two conditions. One is cooperation condition and the other is abort and retry condition. Cooperation condition comes in when T2 finds that T1 is already working on it, and then in that case T2 first tries to cooperate to complete T1's work. And abort and retry condition happens when the data has changed and essentially it needs to refetch the data from the data structure. We'll discuss about the abort and retry in the later slides. So if you think intuitively, essentially we are converting lock to a spin lock. So in the original list we had lock 1, and then right now we have op pointer 1, which is a pointer to an op description. So we are essentially using store conditional using while loop, and then kind of marking the op pointer with a new op description for a process. So when a process is able to successfully mark an op pointer with his op description, then it can be said as equivalent to exclusive access. So the change 2 is, as I told you, it's on the process side. So this is the overall pseudocode, which is like the only pseudocode which is there in the paper. Essentially here we have a procedure called cooperate. It accepts a state pointer, and we are reading so we are using load link to read the state pointer, and we are checking whether the operation is completed or not. So by load linked we are reading the operation in the state pointer, and we are checking whether the operation is successful or not. If not, like, we enter the while loop. So the first thing that we do is we mark the operation as successful, and if the next operation is a read or write on a shared data structure, then we enter this if loop, if condition. So once we enter the if condition, we use store conditional or read load link to read or write to the particular data structure. If the instruction was a write and then the store conditional failed, then in that case we reread the data from the original shared data structure using load link. If the data also doesn't match with what we are trying to write, then we mark the status as failed, and we proceed with the next step. So essentially next pointer is going to be either the next instruction or the previous instruction if it was a failure, and we use store conditional to write to the state pointer what is the next operation that the particular thread is going to do, and finally we read from the state pointer and then determine what is the next instruction. So this last two sentence can be a bit confusing. We'll go over it in the subsequent slide. Essentially this state writing to a state pointer and then reading from the state pointer is done to ensure that state pointer is saving to an auxiliary memory, which is kind of a shared memory which other process can also update. So this is kind of the op description which is kind of globally available for a particular node, and then like other process can read from that op description and things like that. So I think personally I felt that the pseudocode was a little abstract, and I tried figuring out by just constructing a concrete example. So here we have a normal process. We have linked list, which is going to be our shared concurrent data structure, and then we have run function, which is going to have 3 instructions. One is a print hello, and then we have add 5 and add 6. So this would be how a cooperative process would look like. We have the linked list which was there previously. We have the run as well. On top of it, we'll have a state pointer which is initially pointing to null. We have cooperate function, and we have the next instruction. So when we call the cooperate function, the first thing that we do is we load the state pointer with the next instruction, and then we call the cooperate function with the state pointer. So essentially this is just polymorphism and kicking in. But then yeah, what happens in the cooperate function is that we read the op description by load linking to the state pointer. We check whether the status of the op description is success or not. If it's not a success, then we mark it as success. We perform some operation, and if the operation failed, then we mark the status as revert the status as failure. All right. And then what we do is we use next pointer to read the next instruction if succeeded, and we use store conditional to write to the state pointer the next pointer instruction, and then finally we read from the op description what is there in the state pointer. So this essentially is just a while loop going over the instruction one by one. So if there are three instructions, we go over them one by one, and then for each instruction we are saving that instruction to a global memory, so that like other process can also read from there and then like update the status and things like that. But yeah, on a high level the while loop is pretty simple, just a linked list while loop or something like that. So what happens in the middle is something that we need to figure it out. So let's zoom in. Here you can see that op description can either be read or write on a linked list. If it is a read or write on a linked list, then only we enter the if condition. If not, then we can just directly mark it as success, because printing a hello world doesn't involve modifying the shared data structure. So uh, the functions, some of these functions are a little bit abstract, so we'll be covering that in the subsequent slides. But then what we do is essentially we fetch what are the cells that are required for our operation, and we write to the cells using store conditional. If the write failed, and in that case we read the data using load linked, and if we check whether the thing that we have read is essentially the thing that we wanted to write to that place, if not, then we mark the operation as failure, and then we proceed to the continuing the while loop. A quick intuition could be a group project. So let's say we have a shopping cart project which has login, cart and checkout page, and then there is a task board. So nil, right now each of the project is assigned no one, so it's marked as nil. And then there are two devs, Bob and Alice, who are working on that project. So project can be thought of as shared data structure. Bob has got 3 tasks and Alice has got 3 tasks or 2 tasks. And then in the task board we can see that like essentially each block, each of these entries can be thought of as cell 1, cell 2 and cell 3. So Bob's task 1 is going to work on 2 cells, which is 1 and 2, and then Alice's task 1 is going to modify 1 and things like that. So let Bob start first, and surprisingly Bob marked login and cart page, and like after marking that page his process got halted. So say for example he went on a vacation or something, and then now Alice wants to work on login page, but Alice sees that Bob is already working on that, and but Bob has not kind of completed the work. So what Alice would do is Alice would complete Bob's task, and Alice would update both login and cart page by doing Bob's task 1. And after that is done, you can essentially like clear out Bob's task 1 from the task board, and it becomes nil. So now Alice tries once again claiming the login and cart page, and if she succeeded, well she only needs login page. So she tries claiming login page, and if she succeeded, then well and good, she is able to proceed. And suppose now Bob comes back, and then Bob tries to write to the particular shared data structure, and the store conditional failed. So now at this time Bob uses load link to read the data which is already there in the shared data structure. He finds that the data that he wanted to write was the data that is already present in the shared data structure. Now Bob is happy. He can essentially proceed to the next task. But this leaves us with the question that what if Alice's task was modifying Bob's task, and then Bob can't find his update in the shared data structure. So yeah, this would be a scenario where like Alice completed her task, and then like some task modified login page again, and this time it was not something that Bob was trying to update. But in that case, what would be the scenario? The paper doesn't give you a clear description of what is to be done in that scenario. So from whatever whatever that's there in the paper, I think that's where the author kind of brings in the auxiliary memory into picture. So my understanding is that state record is the is a shared memory which is like accessible by all the processes. So if p1 if Bob was to work on login page, and Alice was the person who completed Bob's task, then Alice can essentially mark that operation as success, though uh, so Alice can mark that operation as success. So next time when Bob reads the record, he can first create his state pointer and then check whether somebody has already completed that task. If so, then he can like proceed with this next task. He need not check the entire data to be matching and things like that. The second approach is that you can have an announce array similar to Hurley's approach. So we can have an announce array, and then Alice, if she completes Bob's task, then Alice can mark Bob's task as false, and then like she can proceed with the task. So when Bob resumes his task, he can check whether the announce array is still true or false, and then based on that he can proceed with this operation. So so my thought would be like basically before we proceed reading the data and like checking whether the value matches with the thing that you're about to write. Before that, you can also read the state pointer and then check whether the status is still success, and status is success. If so, you can just ignore this and then proceed with the next instruction. So the second technique that we are going to discuss here is caching method. So essentially this has got 4 steps. The first one is performing on the cache. So if we have a shared data structure, say a linked list, and we want to modify some node, then what we will do is modify a set of nodes. Then what we'll be doing is we try performing an operation on the cached version of the data structure. So if you don't have a particular cell inside your cache, then you essentially load link the cell from shared data structure to your private copy, and you perform all the sequential operation on your local copy. In the validate phase, we verify whether the data in the shared data structure has changed or not. If it has changed, then we abort and retry. If it's not, then we proceed to the next steps. This can be thought of as a performance improvement, which will be discussed when we are discussing about the time complexity of this particular algorithm. And then we have claim. So claim is a step where we are trying to put the op description into the op pointer of a particular cell. So this is the place where we kind of have a mutual this is the place where this can be thought of as the two-phase locking part, where like you incrementally kind of lock each of the cells by putting your op description into the op pointer. One thing you have to notice that in order to avoid live lock, we are just going over the cells in incremental order of their keys. And then finally we have this update step where we perform the update, and then we are clearing out the op description from the nodes. Alright, so previously this was the code we had, and this time we just modified it to have the caching technique steps as well. So as we discussed, there are four steps. The step one will give you all the cells which are required for the operation, and in the step two, essentially we go over each of the cells and then check whether it's still valid or not. In the step three, we claim them in the increasing order, and in the step four, we make the updates. Finally, there is this invariant that no thread is aborted more often than the number of operations successfully completed. So whenever, so it can be seen as like whenever a thread fails, there is someone who actually succeeded in his operation. So if we consider P1's operation as a series of attempts, then in attempt 1, if it aborts, then someone like P2 succeeded, and in the attempt 2, if it aborts, P3 succeeded, and attempt 3 abort, P2 succeeded again, and then attempt 4, if it's a success, then like obviously P1 succeeded. So the number of attempts of P1 is 3, and the number of success overall is like 4. So number of attempts aborts by P1 is always less than the number of successful operations on that superset. How the cells are split? So essentially, it follows the ideas of Lee's fragmentation rule. So Other says that for linked list, there is this natural partitioning where you can partition each cell as each linked list node. And for keys, we can assign keys anything, but then like you can also put the keys as like pointer, address, or something of that sort. The cell structure is essentially three items. One is address to the pointer of the cell. The second is the old data pointer, and then the last one is the new data pointer. We'll be covering that in the subsequent slides. So in order to quickly traverse the cells and like do the operation, you can convert the list of cells into a binary tree and then help in fast traversal. And once you are done with the binary tree operation, I think it can be converted to a binary search tree based on ordering of the keys. And so it can be converted to binary tree, and then like the binary tree can be converted to a sorted linked list for claiming the cells. So essentially it helps in faster searching and retrieval of the cell, and also converting the list to a linked list of sorted order of based on the sorted order of the keys helps you in claiming the cells in the incremental order of their keys. So that will be also seen in the code in the subsequent slides. All right, so we have I have just highlighted the modified portion. So we have cache cells, and S is the number of cells that we will be requiring for our change, and that's just the array size. So and then we have three functions, which is search within the cache cell for like binary search, traversal, and things like that, convert cache cells to a BST, and convert cache cells to a list. So this will be used for like incrementally locking all the entries. And cache cell will be having pointer address to the cell, old pointer, which is original red value, and then new pointer, which is T's version of the value. In the cooperative process, we have like just modified the particular cells. So I think so step one is going to give you a set array of cache cells. We are going to validate those cache cells. Once we have them validated, we are going to convert the cache cells to a list and then proceed with claiming. And once we are done with the claiming, we'll update it. So correctness wise, there are four invariants that are covered in the paper. One is that pointer to the record or pointer is only changed by the thread which is cooperating to complete the associated operation. The multiple threads can work on the shared data structure. And also the third one is talking about creating a directed graph using nodes and edges. So nodes will be the process, and edge would be there only if process 1 agrees to cooperate for the completion of process 2. Since we are kind of locking the items in the incremental order of their keys, it will be guaranteed that it will be acyclic, like the graph will be acyclic. And finally we have this invariant that no thread uses a result of incomplete operation to perform their operation. So I think we can skip this. Okay, now we'll discuss about the performance. So we'll lay down few variables. So t is, as I told previously, t is just the number of steps required for the execution of sequential implementation of the data structure. C is the copying algorithm cost, and S is the number of distinct cells read or written by the operation. So if you see S, I have used it here. So cache cell S, cache cell array size is S. Alright, so now let's go over the copying algorithm. A quick intuition says that we have the total cost as T plus C. We have already seen how like C is more dominating when it is in the case of doubly linked list and things like that. So this is the proposition 5.1 from the paper. So here it talks about copying algorithm for k operation cost around kp into c plus t, and we'll go over the caching algorithm. So caching algorithm, one claim is that s will be always less than or equal to t, which is number of distinct cells read or written will be always less than or equal to the number of steps required for sequential operation. And then there is this variable called alpha. So alpha, intuitively you can think of it like the number of entry points to a particular data structure. Say for example, if there is a linked list and it is used as a backend for queue, then we have the number of entry points to be 2 and alpha is 2. So NQ will add item to the tail, and then DQ will remove item from the head. So for the caching algorithm, the theorem states that the time complexity or the work complexity will be kp into alpha s max plus t max into log s max. So simply said, we can say that it's around t log t, and the paper doesn't give you a exact proof description, but then it just gives you a proof sketch on this time complexity. So we'll see in the subsequent slides how at least t log t is coming into picture, and then how is alpha into s max also coming into picture. So so let's kind of convert piece operation as a series of attempts. So say for example, there were 3 attempts for piece operation to succeed, and attempt 1 and attempt 2 essentially aborted, and then attempt 3 succeeded. So by invariant, for each aborted attempt, there is at least one successful attempt by another thread, say P2 or P3. And if we are able to amortize most of the work done by T1 during the abort, that is charged to the successful attempt, then most of the work done by T1 during the abort is charged to the successful attempt, and that is alpha into S max. Alright, okay. So this is a quick refresher for the recurrence relationship. We know that Tn equal to Tn by 2 plus 1 is the recurrence for binary search, and it is time complexity T log log n. For the merge sort, it is n log n. For the bubble sort, it is n square, and things like that. In order to avoid confusion, I have just converted T to W, and W can be thought of as work. So W of n is equal to W of n by 2 plus 1. It's still log n. And in our case, a caching algorithm should be giving the recurrence of Wn equal to W of n by 2 plus t to get our time complexity bound. So we'll in the subsequent slide, we'll see how this W of n equal to W of n by 2 plus t comes into picture. So if we solve the recurrence w of n equal to w of n by 2 plus t, we get the equation to be like t log n plus c1. And okay, so uh, okay, so let's focus on the bottom side. So here you can see that in the ideal scenario, since we have converted the operation as a sequence of attempts, uh, for the nth attempt, we the total work done on the nth attempt would be the total work done by n minus 1 attempts plus t. T is the sequential cost of operation. Okay, w of n minus 1 would be all the work done by previous attempts. All right, so as we discussed, there are 4 stages in the operation. So one is performing the operation, one on the local copy, which is inexpensive, validating, there is this operation on claiming, and then there is this final operation on updation. So work done by n minus 1 attempts would be ideally n minus 1 into 4 of that units. So let's say the operation takes 4 units for all the 4 steps, then let's keep it as 4 into s or 4 into t. All right, t and s can be interchangeable because s less than or equal to t. All right, so so here you can see that the total work is 4 units, and we discussed that validation is often used as a performance improvement. All right, so after you complete the complete performing the operation in step 1, you go to step 2, which is a validate phase. All right, so most of the time what happens is the thread will fail in the validate step, as like some thread has modified the data. So in that case you do an abort and retry. So most of the time you need not complete all the 4 unit work, but instead only need to complete half of it. So you need not go over 4s, but you just need to complete 2s. All right, since you're only working on half of the work for all the n minus 1 attempts, it can be converted to w of n minus 1 can be converted to w of n by 2. It's like saying 5 people working on sorry, it's like saying 10 people working on half 10 people working half a day is kind of equivalent to 5 people working full time. All right, so it's like doing an internship, and like 10 days part-time internship is equivalent to 5 days full-time internship, so something of that sort. But essentially you get the idea, right? Wfn minus 1, how wfn minus 1 kind of converts to wfn by 2. And t is essentially the cost of sequential operation. And we also discussed that there is this amortization happening, and that comes in place in this particular portion. So so far we have seen like what if the thread fails in validate phase, but there are chances that thread might also fail in the claim phase. So in the claim phase, most likely it is failing due to threads trying to lock from both ends. So as we discussed, alpha is like the number of entry points to a data structure. So if one thread was to enter from head and the other thread was to enter from tail, there is a chance that both of them don't know that they are going to like they are going to uh, conflict with one another. So essentially one of them will succeed but the other will fail. In that case, the failure cost in the step 3 phase is going to be charged to the one that succeeded. So that is why we have wfn, which is the cost for which it succeeded, to be wfn by 2, which is all the previous failed attempts, all the half of the previous failed attempts plus the sequential cost of operation plus the step 3 cost from a failed process. Right, so this gives you t log n plus essentially it should be like alpha minus 1 into s. So no thread is aborted more often than the number of operation gives you a guarantee that wfn by n equal to, sorry, yeah, uh, yeah, so w of n equal to w of n by 2 plus t, and then t log n, we see, like we saw how this recurrence is converted, and then n is essentially kind of equivalent to t because of this invariant, and then yep, that's how that time complexity bound was captured. So on the final notes and future work, the author gives thoughts on like uh, how Q implemented using linked list benefits from the copying, benefits heavily from caching algorithm and compared over copying algorithm. And he also devises a technique, he also discusses on devising techniques to analyze weaker adversary, and then kind of coming up with algorithms, better algorithms based on machine behavior and things like that. He also takes this forward and creates a weight free algorithm on heaps. And then finally he talks about how this approach is flexible enough to give a user like the flexibility of modifying, say, cooperation schema and things like that without violating the correctness. And finally the paper mentions about using other deadlock avoidance techniques rather than just incremental locking of those nodes. All right, I think we have almost concluded the paper, and these were all the four reference papers that I have read for preparing this presentation, and most of the icons are taken from Flat Icon. All right, see you guys in the next week. Bye bye.